Okay, we are now the YouTube channel is on now. So let me first briefly introduce our speaker today, and Dr. Guanxin Li. He's currently a postdoc research associate in the Division of Applied Mathematics at Brown University. He received his PhD from Jinin University in 2021, where his research focused on the development of multi-scale computational model for complex fluid. His research involves the use of many different particle-based numerical methods, such as molecular dynamics, dissipative particle dynamics, and smooth dissipative particle dynamics, to simulate biological system at a different scale. And usually the scales span from the molecular level to cellular, and even multicellular system, and even vascular flows. So through his research, Dr. Guanxin Li already demonstrates that the potential of computational model in bridging the gap between micro and the macro physiological process, including the blood flow, complex fluid flow. So Dr. Li, the stage is yours. Please start your presentation. You can use the full screen if you want.
Okay. Thanks for your introduction, Zhen Li, and thanks for giving me this opportunity to be here to share my previous work in complex fluids and soft matter seminar. The title of the talk is Parallel Modeling of Cell Suspension Flow in Complex Micronetworks with Inflow and Outflow boundary conditions. Here shows some of my collaborator. The first one is Qing Ye, is my PhD supervisor, and another one is Xuejin Li, is another collaborator from Zhejiang University, and George Kandakis is my postdoc supervisor from Brown University. And here is the overview of the presentation. First, I will introduce the significance and the challenges of the current work, and then I will present some models and methods. After the model and methods, I will do some validation from the pure fluids in straight tube and bifurcation, and then go to simulate one capsule, the deformation of the capsule in the straight tube, and finally I will go to the red blood cell suspension. Finally, I will introduce some applications based on the current models and methods. Blood is very important to our health. The left top figure shows the blood circulation in our body. The blood flow provide nutrition and oxygen to the tissues, and at the same time, it will take out the metabolic waste by vein. A lot of disease is related to the sickle cell, for example, malaria and diabetic Gaucher disease. The in vitro is also an important way to investigate the blood flow. This machine, the right bottom machine, is used to separate the circulating tumor cell. And inside this machine, a spiral tube is used to inlet the blood flow, inject the blood flow from the inlet, and the purple particle represents the circulating tumor cell. The large size CTC will move to the inside of the tube and the left force, and the small size cells such as red blood cell, platelet will move to the outside of the tube. Then it will achieve the separation of CTC. In addition to the in vivo and in vitro, the in silico is also an important tool to study the red blood cell. There are mainly include three methods. First is the mesh-based method, for example, FFM, FDM, FEM, and then particle-based method, such as SPH, DPD, and SDPD. And finally, the third one is a hybrid method. For example, LBM, we choose a DPD or SDPD to simulate the red blood cell. Why we choose these two methods? Because the DPD is a bottom-up method. It comes from MD. And the SDPD method is a top-down method. It comes from Navier-Stokes equation and add the mesoscopic fluctuation. These two methods are good at solving the mesoscopic problem. And the diameter of the red blood cell is about 8 diameter. So the size of the red blood cell and these two methods match with each other. So we choose these two methods to simulate the blood flow. For particle method, there are some challenges. First one is the boundary condition. Boundary conditions in particle method previously include solid wall boundary condition and periodic boundary condition. We always simulate the red blood cell suspension or cell suspension in the street tube by periodic boundary condition. However, how to develop the accurate inlet and outlet boundary condition still remains unsolved issue. Another challenge is the computational cost. In contrast to the mesh-based methods, the particle-based method operate within the framework of Lagrange systems. The development of an efficient parallelization framework is very important for the efficiency. Then I will introduce the model and the methods. Our model and method is most dispersive particle dynamics and immersed boundary method. Oh, sorry. When we simulate the red blood cell, we assume the red blood cell is filled with the plasma, and because the velocity of the flow is very low, so we assume the system is incompressible and isothermal. So we can get this incompressible Navier-Stokes equation. The first one is mass equation, and the second equation, second one is the momentum equation, where the rho is density, v is the velocity, p is the pressure, and eta is the viscosity, and J is the external force to drive the flow, and F, this small f is the RBC cell force. This force is the interaction between the fluids and the red blood cell. We can compute the cell force by the membrane particle within the supported domain of the fluids particle. At the same time, we can compute we can update the coordinate of this large of the membrane particle large X by the fluid particle within the supported domain of the cell membrane particle. The left figure shows a simulation domain. In the simulation, before we discrete the Navier-Stokes equation, we first discrete the simulation domain. We will discrete the simulation domain into 4 kinds of particles. First is we will discrete the wall particle the wall to wall repulsive particle, and we will also add a ghost particle. We there are 4 kinds of particles. First is a repulsive particle, membrane particle, fluid particle, and ghost particle. A repulsive particle is provided the repulsive force to avoid the penetration of fluid particle and cell membranes. The membrane particle is the particle on the surface of the red blood cell. The fluid particle represents the fluids. For example, plasma, and ghost particle, because you can see when the particle close to the wall, the supported domain will be incomplete. So we provide this ghost particle will provide the entire supported domain of the particle within the which located on the surface, close to the boundary of the tube. And then we will use a kernel function to represent the delta function to let the simulation more smooth and continuous. And then we use the particle approximation to substitute the kernel function to get each terms in the Navier-Stokes equation. After this discretization, we can get the SDBD IBM model formula, where in the SDBD IBM model, Fc is the conservative force, and the Fd is the dissipative force. Fc is related to the coordinate, related to the pressure, and the Fd is related to the velocity and the coordinate of the particle. Fr is the random force, which comes from the mesoscopic fluctuation, and Fg is the global force, which used to drive the flow, and Fb is the cell force. This is the discretization of the IBM and SDBD. We update the membrane particle of red blood cell by the fluid's velocity within the supported domain of membrane particle, and at the same time we can get the cell force. The cell force include deformation force and aggregation force will come from the membrane particle. This is the formula in the SDBD formula. We also, when we consider the cell deformation and aggregation, the cell surface is we use the membrane particle and some triangular to represent the surface, the membrane of red blood cell. The particle is connected by the triangular, and when we compute the deformation force of red blood cell, we will consider these 4 kinds of energy. First is the stretch energy, and then the bending energy, and UA is the conservation of surface area, and UV is the conservation of volume, because when the red blood cell flows through the capillary, because the capillary diameter is less than the diameter of red blood cell, so the red blood cell need to squeeze through the capillary. So the stretch energy is mainly represent the stretch deformation of the red blood cell, and UB represents the bending deformation of the red blood cell. We also use the motion potential to calculate the aggregation force between the 2 cells. if in the multipotential model, when the equilibrium distance between when the distance of the center of the two cell greater than the equilibrium distance, the cell will have a adhesive force. When it less than the equilibrium distance, it will have a repulsive force in this model. Then I will introduce the solid boundary condition in the model. The solid boundary condition in our model mainly provide the repulsive force to avoid the penetration of the red blood cell and the fluids. This is the formula. Next, I will especially introduce the inflow outflow boundary conditions in this work. This work published in the Journal of Computational Physics. In the inflow outflow boundary condition, we divide the simulation domain into three parts. First is the inflow boundary condition, inflow domain, main simulation domain, and the outflow domain. In the inflow domain, we apply the inflow boundary condition. It is used to fully generate the red blood cell and particle to the main simulation domain. And the mass and momentum in this domain is conserved. And the main simulation domain is used to observe the biomechanics and fluid dynamics. And the outflow domain is used to decide when we should delete the particle of red blood cell in the system, from the system. First, I will first introduce the inflow boundary condition. In the inflow boundary condition, we should consider two things. First is the particle inflow condition. When figure A shows the particle A traverse the boundary between the inflow and main simulation domain to the main simulation domain from n time step to n+1 time step. The next step, when the particle A pass through the boundary, we will copy the same particle A prime to the main simulation domain. The physical parameter of A prime is the same as particle A. It's very simple for the particle flows from the inflow domain to main simulation domain because it can complete the whole process by one time step. But if we consider the red blood cell flow from the inflow domain to the main simulation domain, it's a little bit complicated because the cell has structure, so it cannot move from the inflow domain to the main simulation domain only one time step, maybe 1,000 time step, or more than 1,000 time step. So how we deal with the cell flow from the inflow domain to the main simulation domain? Once in our inflow outflow boundary condition, in this figure A, we show the cell A flow from the inflow domain to the main simulation domain. Once one particle of the membrane of cell A pass through the boundary, we will copy the whole red blood cell to the simulation domain. But how to update the two parts of the red blood cell located the boundary between inflow and main simulation domain. Under the periodic boundary condition, if cell A pass through the boundary, will move the the particle of membrane A already into the main simulation domain to the left side of the inflow domain, and the new red blood cell A prime. We will consider to update the cell A prime into two parts. First, we copy the same physical parameter as cell A, and we will compute the red part of the part in the simulation domain by the fluids in around the prime A prime. This is the movie when the red blood cell flow from the inflow domain to the main simulation domain. The green color represents the red blood cell in the inflow domain, and the red color represents the cell already in the main simulation domain. We can see. We can see when this cell pass through this boundary, there will be two cells in this location. One is this one, already into red color, and the previous one is this. The previous cell will move to the left side of the inflow domain under the periodic boundary condition. For outflow boundary condition, for the particle outflow boundary condition, if figure A shows the how to deal with the particle when the particle A traverse reach to the right boundary of the simulation of the outflow domain. We just delete the particle if the particle flow out of the system, but we need to consider the conservation of mass and moment. How to conserve these two variables? We will choose a target region RT as the same. We let the outflow domain. These two, the mass and the moment is the same as the target region. In the straight tube, we will choose the target region from the main simulation domain. But for the bifurcation, it's very difficult to do the same way. The same way, we will choose the adjacent area as the tangent region RT. We also apply two force for the particle within the outflow domain. In order to speed up the, there are another challenges. Computational cost. In order to speed up the simulation, MPI framework is constructed in our simulation. This framework is based on the master and slave structure. The main master is used to divide the simulation domain and assign the task and receive the simulation result from the slave thread. The slave thread include three kinds of three types. First is the cell slave thread. The cell sleeve thread is used to calculate the deformation and the aggregation force of the cell. But the inflow for the inflow thread, slave thread is used to compute the inflow domain. It will update the coordinate and velocity and some other properties of red blood cell and fluids. And the hybrid slave thread is used to simulate the main simulation domain and outflow simulation domains, fluids and fluids particle and cell particles velocity and coordinate. Then we also check the efficiency of the parallel efficiency. We first test the efficiency in this macrovascular by serial code and this parallel code. And under the same condition, we can see the performance of for the serial code. It used 3,100 core hour, but for the parallel code, it only use 200 core hour. So the efficiency of the parallel code is more than, it's about 30 times than the serial code. This is the algorithm of the current method. First, in our SDBD IBM model, we first update the memory coordinate of red blood cell. And then when we update the fluid coordinates, after update the coordinates of red blood cell and the fluids, we will consider the inflow outflow boundary condition. And then we update the fluid density and pressure. And after that, we will predict the fluid velocity and update the resultant force. And finally, we'll consider the inflow boundary condition. But how to start the system? When we start simulate the red blood cell blood simulation, we first create the system. Create a system includes we first loading configuration. For example, we need to prepare the red blood cell and the fluids and the geometry. And then we need to setting the parameter and dividing domains in the creating system. After creating system, we need to decide when we need to drive the system. We apply the external force to drive the system. And this updating system is the main part of the simulation. In this part, we will construct the linked list and perform the velocity alert algorithm and sending the result to the main slave. Finally, we will output the system and finally delete the system. Here I will show the computational performance by the current model and method. This is a microfluidic chip I designed in the simulation, and that shows some overview of the simulation result. We can see in this compacted geometry, the cell has some when the cell passes through the spiral channel, it has some deformation, and the distribution of the particle in this channel, in this microfluidic chip is uniform. This is a movie of the blood flow in the microfluidic chip. Oh, after the method and the models, we did some validation. First, we validated the fluid velocity profile in the inflow domain at the inflow region and the outflow region, and we compare the simulation result over time with a theoretical solution. And the black one is the current result, and the red one is the result from periodic boundary condition, and the line is the theoretical result. We can see the inflow outflow boundary condition result is consistent with the two other methods. And we continue to validate the velocity profile in this bifurcation. This is the geometry of the chip. And we check the velocity profile at the feeding vessel and two branch vessel, and compare the velocity profile with the nectar result and the DPD result. And we can see the consistency is good. After check the fluid velocity, and we check the deformation of the capsule in the straight tube and different velocity. We put the capsule in the inflow region and apply some flow to drive the system and check the deformation of the capsule. And we compare the cross section. We compare the cross section of the capsule with a different result. This is the current result. And finally, we go to the cell suspension level. We compare the effective viscosity between inflow outflow boundary condition among the inflow between the periodical and draws result. After the validation, I'll introduce some application based on the current method and models. Figure A shows a microfluidic chip in the industry to separate the blood plasma from the blood flow. The upside is the injection is the inlet. When we inject the blood flow from the inlet, the red blood cell and the cells can flow from the left side of the tube, and we can get the plasma product from the right side. But we can see there are still some red blood cell. The cells flow through the plasma. We want to avoid the cell flow into the right side. Based on this, we also designed a microfluidic chip in our previous work to separate the plasma. This is the geometry of our design. We inject the red blood cell, the blood flow from the left side, and we want to get the plasma from this 5 branches. And the red blood cell will flow through the outlet. We can see there are no red blood cells flow through the plasma, so we can get the plasma product from this branch channel. And this is the thrombus formation in a spiral, in a curved channel. And we can see the formation of the thrombus. The yellow color is the clot already formed on the surface of the vessel, And the blue color is a platelet. We can see at first there are no platelet adhere to the clot. But there are more and more platelet adhere to the clot over time. Finally, it will block the flow. And we also simulate the tumor cell adhere to the vessels in this complicated network. We can see the blue one is the circulating tumor cell. When the tumor cell transfer to the tissues, first it need to adhere to the vessel and then traverse to the tissue. In this work, we first simulate the adhesion between the tumor cell and the vessel. You can see the tumor cell is easily to stay in the bifurcation of the network. At this bifurcation, it will block the blood flow. And the last case is when COVID-19, there are some observation in vivo from the clinical, and it shows some blood cell will adhere each other to cluster. So we simulate the blood cell cluster in this complicated network. You can see this is the blue one is it's a cluster of white blood cell. We can see in this capillary, it is easy to block the blood flow in this small bifurcation. So if the cluster, if we increase the size of this cluster, it maybe block the large vessel in our body, and it is more easily to form the thrombus to block the blood flow and cause some disease in our body. This is the conclusion of this talk. First, we develop a framework of SDBD IBM with inflow, outflow boundary conditions for simulations of a large numbers of cells through complex macro networks. And second, in order to reduce the computational cost, a MPI parallel framework with a master-slave configuration is developed, where a master thread divides the simulation domain or assigns the simulation tasks to 3 types of slave threads. Oh, sorry. Include the cell slave and inflow hybrid slave threads. And finally, I will introduce several applications such as cell suspension, thermos formation, and vessel occlusion. Oh, thank you. That's all. Any question?
Thank you, Guanxin. If our audience have a question, you can unmute yourself to ask a question to Dr. Ni directly. Guanxin, maybe I can start with one question I have is
okay.
I know previously Shujin, about 2015, he also developed inflow outflow boundary condition
Yes.
using the DPD and implement in LAMS. So now here you are using SDPD and couple with the immerse boundary method to do the similar implementation. So which part do you think is the implementation is better than that one? Because
Oh,
you develop this method, it's about 5 years later than that one, right?
oh yes. I think the main difference between the two works is the when we deal with the inflow for the red blood cell. In that work, when the cell passes through the boundary between the inflow and and the main simulation domain, I remember they put the new cell. They when they decide when the new cell copy to the main simulation domain, when the center of the red blood cell A pass through the boundary, so it will suddenly add one red blood cell to the main simulation domain. It will destroy the fluid field in the main simulation domain because it's not continuously to flow through the boundary. Yeah, this is the one difference. And another difference is the outflow boundary condition. In the outflow boundary condition, we consider two. We consider attached region in the simulation in the main simulation domain or the inflow domain, and we also add two force to control the mass conservation and the momentum conservation. And yes, these are the two main differences between the previous work.
Okay, so I have another question. Is when you now you have several system, a subsystem to do the entire simulation, right? You consider to implement the do the test the power efficiency. Then you have to decide. For example, you have 100 CPU. You need to decide how many CPU distributed to the each of the subsystem. So this is manually determined by the user, or you have some algorithm to can determine what's the best.
I have the algorithm in the creating system, and in this creating system, we will compute the we will decide how to assign the threads to each simulation domain. Depends on the it depends on several conditions. First is the number of the cell and the length of the tube. Yes.
Okay, so you use some algorithm to automatically determine the resource
Yes.
distribution to subsystem, right?
Yes, you don't need to decide by yourself.
Okay.
There one algorithm in the creating system in the dividing domain in this part.
Okay. Any other question from our audience? Okay, if there's no more question, we can end the seminar today. And thank you, Dr. Ni, for your very this cover a lot of different topic. And I think the most important part is how you generate this inflow outflow boundary condition in a parallel case.
Okay, thanks for your invitation. Thanks everyone. If